Well, thank you, Peter, for the introduction, and thank you for the organizers for inviting me, and thank you everyone for being here. So I will speak about joint work with Eugene Gorski and Monica Vasserani, also from Davis, where we studied the geometric representation theory of rational Cheretnik algebras and other closely related algebras using the geometry of the parabolic Hilbert schemes of the type. So let me start by the geometric part of the story. I will consider a plane curve in a C2, which is just given by the zeros of some polynomial. And for simplicity, I will assume that 0 is in this curve. In other words, this polynomial doesn't have constant terms. The Hilbert scheme of this curve, KC, is the modular space of codimension K ideals inside this algebra of functions. So just all these ideals form a scheme, and we call it the Hilbert scheme. For simplicity, I will focus on the punctual Hilbert scheme, which means that now I look at codimension K ideals inside the local algebra of germs of functions around 0, which is just formal power series in X and Y, mod out by the ideal generated by F. Let me give a few examples. So this example is when 0 is a smooth point. Then, well, by definition, this means that this algebra is just formal power series from one variable. And the Hilbert schemes in this case are not very interesting. It's just, well, the ideal generated by T to the K, right? So this is not a very interesting algebra, I guess. More interesting story happens when 0 is a singular point. Let's take, for example, the case when 0 is a node singularity. Let's say that C is given by the equation X times Y is equal to 0. So it's like the union of the two axes. Then for K is equal to 0 and 1, we just have a point. If we want to study Hilbert schemes of more points at 0, then what we can do is we can draw all the monomials in this algebra. So I have, oh, sorry, 1, x squared, x cubed, and so on, y squared, and so on. I already modeled out by x times y, so I don't have anything in this part. So we can see, for example, that the ideal generated by x squared, y squared has codimension 3. I just get rid of everything to the right of x and up y. And I modeled by one more relation to make it have codimension 2. And we can see that Hilbert scheme of 2 points is P1. If we go for the Hilbert scheme of 3 points, then, well, we have this monomial ideal generated by x squared, y squared. We can see that we also have these two monomial ideals. Moreover, if we mod out by x squared and y cubed, we have an ideal of codimension 4. One more relation, we move to codimension 3. And note that when we set, for example, alpha is equal to 0 here, when we set alpha is equal to 0, what we get is just the ideal generated by x squared, y squared, which I have already. So in other words, if I consider this family together with this ideal, and also when I set beta is equal to 0, what I have is this ideal. This form a copy of P1. Similarly, if I consider now this family together with this ideal and this ideal, this also form a copy of P1. So what I have is a union of two P1s that intersect at a point. And in general, the Hilbert scheme will be a union of K minus 1 P1s that intersect at a point in this shape. So it's dual to the type A quiver. So here I have K minus 1 copies of P1. So when the curve is singular, I get more interesting behavior here. I will, however, not go to nodal singularities. I will fix coprime integers and an M and consider the cost singularity C, which is given by the equation x to the m is equal to y to the n. let's take an example. When m is equal to 2 and n is equal to 3, I can parameterize this curve. So the algebra of germs of functions around 0 is just this formal power series in t squared and t cubed. And from here, we can check that this Hilbert scheme is, well, is a point for k is equals 0 and 1, and p1 for all larger k. So this is much more manageable than what I had before. And moreover, it is a fact that when C is irreducible at 0, then this family of Hilbert schemes stabilize for large enough k to something called the compactified Jacobian of the curve C. I won't go into there. And a theorem of Altman, Clement, and Jarobino says that if C is irreducible, then these Hilbert schemes are actually irreducible, unlike the previous example that we had. And I will want to consider all these Hilbert schemes at once. So if I don't put a superscript, I just mean the disunion of the Hilbert schemes for all k bigger or equal than 0. Now, in the title, I have these parabolic Hilbert schemes. I should define what those are. If I have an ideal inside this algebra of germs of functions, I have that the dimension of I mod xi is precisely equal to n. Remember that here I am dealing with the curve x to the m is equal to y to the n. So I can consider all those subspaces in I mod xi, which are stabilized by the action of y. In other words, I can consider all chains of ideals of length n, where the last ideal is x times the first ideal. And I want each one of these ideals to have codimension 1 inside the previous one. And similarly to what I did before, I will consider just a disunion of all these parabolic Hilbert schemes. That's when I don't write a superscript in here. And let me emphasize that even when the Hilbert scheme is relatively simple, this parabolic Hilbert scheme can be more complicated. Let me give an example, and I guess you'll see my ceiling for a little bit. So in this case, when I have C, which was the curve x squared is equal to y cubed, well, I always have a projection from P Hilb k plus n to Hilb k. Just pick up the first ideal, and let's see what the fibers are. Let's take, for example, the case when this ideal I is generated by t to the k. Then the ideal I mod xi has a basis, which is t to the k plus 2, t to the k plus 4. The action of y that we can identify with t squared will just send t to the k to t to the k plus 2, and so on. This is a regular nilpotent inside SL3. So the fiber over this point is a single point. Okay? However, if I consider the other monomial ideal that I have here, if I now have that I is the ideal generated by tk plus 1, tk plus 2, one can check that the ideal I mod xi is going to be spanned over C by tk plus 1, tk plus 2, tk plus 3. And the action of y is now going to send tk plus 1 to tk plus 3, everything else to 0. The fiber over this point will be the Springer fiber for this nilpotent matrix, which is a union of two P1s that intersect at a point. So this map is not flat, and the geometry of the parabolic Hilbert scheme is more complicated than that of the usual Hilbert scheme. Okay. And to make my life even more complicated, because why not, I will consider more general cases of these parabolic Hilbert schemes, if I have a weak composition of n, let me remind you that this means that the sum of the gamma i's is equal to n, and gamma I is bigger or equal than 0. I allow for some of them to be 0. I consider the parabolic Hilbert scheme of gamma to be just all those chains of ideals, where again, the last one is equal to x times the first one. The length of this chain is precisely the number of elements in my weak composition. And what my weak composition is telling me is the codimension of an ideal inside the previous one. So for example, if gamma here is just 1, 1, 1, all ones, then this P Hilb gamma is just the P Hilb I had before, because that's what I had before. The codimension of each one is at the previous is 1. And when gamma has a single part, which is equal to n, then this parabolic Hilbert scheme, P Hilb gamma, is just the usual Hilbert scheme, because I just need to choose one ideal, and the next one will be x times the ideal I had before. And if CRN denotes all weak compositions of n with exactly r parts, and it's crucial here that I allow some of these parts to be equal to 0, I consider the compositional parabolic Hilbert scheme to be just a disunion over all these weak compositions of n with exactly r parts of these parabolic Hilbert schemes. So this looks a bit weird, but one of my points is to convince you by the end of this talk that it's actually completely natural to consider this compositional parabolic Hilbert scheme from a certain point of view. Now, the Hilbert scheme itself is an invariant of the curve and 0 in the curve, but to define these parabolic Hilbert schemes, I need to choose x. So I have that the last ideal is x times the first one. I could have chosen the other projection to the y-axis, and I can also define those parabolic Hilbert schemes. I will need them eventually. So I have P Hilb y. Well, now the dimension of I mod yi is equal to m. So here I just have m. And the compositional parabolic Hilbert scheme in the y direction is just, I now take all weak compositions of n. So just same definitions, replace x by y everywhere. And another observation is that we have an action of a one-dimensional torus on this curve. And since 0 is a fixed point, this action is going to lead to all the Hilbert schemes that we are considering. All the punctual Hilbert schemes, I mean. So we have an action on the Hilbert scheme, on the parabolic Hilbert scheme, and on the compositional parabolic Hilbert scheme, both in the x and in the y directions.
Jose, ask
Yeah?
a quick question. Can you realize the compositional parabolic Hilbert schemes as also fixed components of the action on just the ordinary parabolic Hilbert schemes?
I think the answer is yes. If I understand your question correctly, the answer is yes. I mean, not the entire compositional parabolic Hilbert scheme, I think, but each one of the parts you can do.
Yeah. Okay.
Yeah. Okay. Any other questions? Okay. Now I have like half of the ingredients I need to give you the main theorem, but I'll give you the main theorem anyways and then fill in the details. So the main theorem, which is joint work with Eugene Gorski and Monica Vasserani, well, recall that we have this curve, this nodal curve, this cusp, where M and N are coprime. Then I have actions of interesting algebras in the equivariant homology of the different parabolic Hilbert schemes. Namely, I have an action of the rational theoretic algebra of type A with parameter M over N on the equivariant homology of the parabolic Hilbert scheme normalized in the x direction. I have an action of the spherical rational theoretic algebra on the equivariant homology of the Hilbert scheme, not parabolic here. And there is an action of the quantized Giesecker algebra that I will define, and I will also define these algebras on the equivariant homology of the compositional parabolic Hilbert scheme. And let me point out that here I am normalizing in the y direction. So these two are different, and that's not a typo. In all these cases, what we get is an irreducible representation that is highest weight, and we can say exactly which irreducible representation this is. Now, at this moment, this theorem doesn't say anything. I mean, it says that there's an action of an algebra on a vector space. So I need to tell you what are these algebras, and I will also explain how to get these actions. Okay. So now we move on. We had the geometry. Now we move on to the representation theory. This is the geometry, physics, and representation theory seminar. So let's move on to the representation theory part. Let's skip physics for the time being. Okay, so I need to tell you what these algebras are. Let me start with the rational theoretic algebra, and I have the statement of the theorem here just for us to keep our goal in mind. Okay, so the rational theoretic algebra, it's very explicitly defined as the equation of a semi-direct product algebra. And let me just remind you that this means that if I want to move an element of Sn past an x, I have to act on the index. And same for y's. By some relations, the relations are that x's commute, y's also commute. What is interesting is when I try to move an y past an x, I pick up some terms. And these terms are going to depend on two constants, t and c, which are complex numbers. Well, the commutator of yi with xj when I is different from j is c times the permutation ij. And the commutator of yi with xi is t minus c times the sum of all these permutations ij. For example, when I have that both t and c are 0, I have that h00 is just, well, I have now commuting x's and y's, semi-direct product with Sn. When t is equal to 1 and c is equal to 0, what I get is differential operators on c to the n, semi-direct product with Sn. So here I just have, I mean, all these c parts go away, and I just have that the commutator of yi with xi is 1. And well, presenting an algebra by generators and relations is my second favorite way to present an algebra. My favorite way is to give you a faithful representation of this algebra, which is what I'm going to do. When t is equal to 1, I can also define the theoretic algebra via its polynomial representation, which means that the algebra acts faithfully on polynomials in n variables. The action of W of the symmetric group Sn is again just by permuting the variables. The action of the elements xi is just by multiplying by xi. The very interesting part is the action of the yi's, which act by these so-called Dunkel operators. This is just a partial derivative with respect to xi. And one can check that if I have a polynomial, I apply this operator, the result will be divisible by xi minus xj. So this makes sense when applied to polynomials. And the theorem here is that these operators satisfy the same relations as the rational theoretic algebra and no more relations. So we have a faithful representation. Okay. And this polynomial representation, well, most of the time is irreducible, but it always has a unique irreducible quotient, which is what my equivariant homology will be at the end. When I have that the value of c is m over n with the GCD is equal to 1, although this is, I will expand on how essential this hypothesis is later, I will just denote this unique irreducible quotient by Lm over n. Or if I need Lm over n, or sometimes, just to emphasize that the rank of the group is n, I will denote it by this. Okay, so that is what the rational theoretic algebra is. I have two families of n generators and the symmetric group that satisfy some relations. If I want to give an action, I need to construct these operators in the equivariant homology of this parabolic Hilbert scheme. The action of Sn is classical. It's given by correspondences. So I have, let's say I can skip the ith ideal and I have a map from that variety to just P Hilbert I and I plus one. And I just do correspondences there. What is more interesting is the action of x's and y's. Well, note that we have a very natural map from P Hilbert. Here, remember that K is the codimension of the first ideal in this chain. Well, I can just take this chain and move it a bit to the right. I just literally just shift this chain. This gives me a map between parabolic Hilbert schemes, and therefore I have a map on equivariant homology. Now, this T is definitely not invertible. However, it is an isomorphism onto its image. Its image is given by those chains of ideals here, where the next to last ideal is divisible by x. Then I can just divide the last two ideals by x and move them back to the left. And one can check that this is the zero locus of a section of a line bundle in P Hilbert K plus 1, K plus 1 plus n. So I have the Gisin map on equivariant homology that, well, technically it goes from here to the equivariant homology of the image, but this T map is an isomorphism onto its image. So I can just put it back and I have this map. Now I have given you the action of Sn and two more operators. Turns out this is enough to generate the entire theoretic algebra. I gave you the presentation of the theoretic algebra with 2n generators plus the symmetric group because that's the more digestible one. It's not the most economic one. You don't need all x's and all y's to generate the theoretic algebra. You need a single x. Then acting with the symmetric group, you can generate all other x's, and same with y's. Turns out that the action of T corresponds to essentially x1, well, x1 with this cosθ element, that's fine. And the action of lambda, which was this Gisin map, corresponds essentially to the action of y1. Together with Sn, these already generate the theoretic algebra. So to prove that there is an action of the theoretic algebra, what we should do is to show that these operators T lambda and Sn satisfy the relations of the theoretic algebra. That's not exactly what we do. What we do is we compare geometric information on the homology of the parabolic Hilbert scheme with algebraic information on this representation Lm over n, as follows. So on the equivariant homology, we have the fixed point basis in equivariant homology. The action, and here is essential that M and N are coprime. This variety has isolated fixed points, which are given by chains of monomial ideals. On the algebraic side, we have a basis of non-symmetric Jack polynomials that was studied by Stephen Griffith like 10 or 15 years ago, something like that. And we can match this basis. We can match this basis and we can very explicitly describe the actions of all these operators in this basis. And that's how we see that the two actions have to coincide.
Oh, Jose, can I ask you a question?
Hmm?
Can I ask you a basic question?
Sure.
Just for the parameters of the rational theoretic algebra, the ones you're considering 1 and m over n, where you described it as a semi-direct product, does it simplify particularly for those parameters, or mainly you need them for the action?
You mean for the, sorry, this thing?
Yeah, exactly.
No, it doesn't simplify particularly for these parameters. What we need, so essentially, this T and C you can always rescale by a non-zero complex number. So I can say either T is 0 or T is 1. And these parameters M over N are, to say it in a way, the most interesting parameters. For most parameters, this representation will be simple. It won't be simple when C is a rational number with denominator less than or equal to N. We need the denominator to be exactly N to have both these things defined, the fixed point basis and the non-symmetric Jack polynomials. That's where this parameter comes into play. Not really with the algebra. The algebra doesn't simplify too much, but the representation does.
Okay, thanks. Great.
Okay. And we also have, yeah?
José, I also have a quick question. This parabolic Hilbert scheme, is it I mean, it's equivariantly formal or something, right?
Yes, it is. Yes.
Or that's kind of implicit in what's going on here to some extent, or?
We prove that it is equivalently formal.
Okay.
Yes.
Okay.
Yes. Yeah.
Okay.
Yeah. But yeah, definitely it is equivalently formal. Yes. Thank you. Yes.
Okay.
Okay. And just to match up geometry with algebra, we have tautological line bundles on this parabolic Hilbert scheme because we have chains of ideals. So I can just take line bundles where the fibers are successive subquotients. And I have intersection product with, I guess this should say, Chern classes of tautological line bundles. With Chern classes of. And this match up with the action of the so-called Dunkel-Obdam operators that were also studied by Stephen Griffith when he defined his non-symmetric Jack polynomials, which in the Theoretic algebra is defined to be xiyi minus c times the I just Murphy element in the symmetric group. Turns out that these Dunkel-Obdam operators act diagonalizably on this LM over N, and these non-symmetric Jack polynomials are precisely the common eigenvectors for these Dunkel-Obdam operators. And in all this slide, it is essential that M and N are coprime. Otherwise, I don't have a fixed point basis because the action won't have isolated fixed points. And I won't have this basis of non-symmetric Jack polynomials. It just won't be defined. Okay, but this takes care of part A. Moving on to part B that says that there's an action of the spherical Theoretic algebra. This is a formal consequence of part A. The point is that we have this map from the parabolic Hilbert scheme to the Hilbert scheme. Oops. We have this map that just picks up the first guy in the chain of ideals. And this map identifies the homology of the Hilbert scheme with invariance on the homology of the parabolic Hilbert scheme. And the spherical Theoretic algebra is defined to be precisely the corner algebra for the trivial idempotent in Sn that belongs to the Theoretic algebra. So part B is really a formal corollary of part A.
Can I ask a question?
Yeah.
You said that this identifies cohomology of Hilb with some invariance inside P Hilb, cohomology of P Hilb.
Hmm?
What did you mean by that? Invariance with respect to?
Oh, we have the action of Sn that belongs to the Theoretic algebra, right? We have an action of Sn via correspondences, and I mean that.
I see. So it acts on. It doesn't act on. It acts on homology of P Hilb, but is that right?
Yeah, it acts on homology of P Hilb. It doesn't act on P Hilb itself. It's like Springer theory. Yeah.
I see. Good. Thank you.
Okay. Any other questions before I move on? Okay, now part C in a way is also a formal corollary of part A, but we need to work much harder to say it. Remember that Parsi says that there's an action of the quantized Giesecker algebra and the equivariant homology of this compositional parabolic Hilbert scheme. I need to tell you first what this quantized Giesecker algebra is. Well, to tell you that, I'll tell you first of all, what it quantizes. The Giesecker moduli space depends on two parameters and an R. Is the moduli space of rank R torsion shifts on P2 with second Chern class equal to N, and we have to fix that trivialization at infinity. The way I think about these things is in purely linear algebraic terms. We can see that this is isomorphic to the following quiver variety. I didn't draw the quiver, I will do it right now. So I have A and B are n by n matrices. And I and J are R by n and n by R matrices. So what I have here is a cotangent bundle of the representation space of this quiver. This equation, which is known as the ADHM equation, is a moment map equation. So I have an action of GLN on this space. And what I do is I do Hamiltonian reduction. I think it's 3 bars, I don't remember. With respect, well, I do GIT Hamiltonian reduction, so I have to pick stability condition given by the determinant at the level 0 of the moment map by the action of GLN. So this is a quiver variety for the frame Jordan quiver, essentially. For example, when R is equal to 1, I have that M and 1 is the Hilbert scheme of M points in C2. That's the linear algebraic description of the Hilbert scheme. And when R is equal to 1, I have M1R is the cotangent bundle on PR minus 1 cross C. And the algebra ACNR quantizes the algebra of global functions on this Giesecker moduli space. Well, we got the Giesecker moduli space using Hamiltonian reduction. It is natural that we get this quantized Giesecker algebra using quantum Hamiltonian reduction. And that's precisely how we define it. So here R, as I had before, is the representation space of this frame Jordan quiver. I have an action of GLN, and I do quantum Hamiltonian reduction on differential operators on this vector space. For example, going back to the classical examples I had on my previous slide, when R is equal to 1, what I have is a spherical rational theoretic algebra. This is absolutely not obvious. It's a theorem of Gann and Ginsburg from 16 years ago. And when n is equal to 1, this is slightly more believable because the classical space is cotangent bundle on PR minus 1 cross C. The quantization has to be differential operators twisted by C, where the twist happens only on the PR minus 1 part. So if you want, when C is an integer, I just have differential operators on a line bundle. Okay. And this is a perfectly fine definition of this Giesecker algebra. The problem is that if I want to define an action, there is no known presentation of this algebra using generators and relations. You can try to get generators, I guess, but it is, well, generators shouldn't be too hard, but the relations are definitely hard. And well, even in the case R is equal to 1, what we had to do, we had to build a bigger algebra, the full theoretic algebra that we understand using generators and relations, and then take invariance.
So can I ask, does the compositional, so this is the guy that acts on the homology of the compositional Hilbert scheme. Mm-hmm. When R is 1, I forget the meaning of R. And when R is 1, what is this Hilbert scheme?
Oh, when R is 1, I only have one composition, which is just n, right? Or m in this case.
Mm-hmm.
And in that case, this compositional parabolic Hilbert scheme is just the Hilbert scheme.
The fiber is a point. The fiber of this map is a point.
The fiber of this map is a point. Yeah, yeah.
Okay, okay. Cool, thank you.
Okay. However, we can solve this problem using recent work joined with Pavel Ettinghoff, Vasily Krylov, and Ivan Losev that constructs representations of the Quantization algebra, starting with representations of the full rational theoretic algebra. And you can see that here I have a flip in the parameters. This is not a mistake. This is the way it should be. And that explains why here I have y instead of x. This representation, Ln over m, is the equivalent homology of the parabolic Hilbert scheme in the normalized in the y direction, which is a representation of the theoretic algebra of Sm, not Sn. And now this goes back to Joshua's question from before, because we can decompose this invariance in the tensor product as the direct sum over all compositions of M of invariance under the S gamma action, where this is a parabolic subgroup in Sm. And each one of these parts is precisely the compositional parabolic Hilbert scheme where I fix this composition. This composition gamma. And this implies this part C. And not only that, but we have a bit more information on how the action is given. So there is a quantum moment map, which is given by the residual action. I had this R part in the quiver variety. So I have an action of GLR, this residual action of GLR. There is a quantum moment map from the Lie algebra GLR to this Quantization algebra, so that every module over the Quantization algebra becomes a GLR representation. This representation that we just constructed is locally finite, and the weight spaces are given precisely by the equivalent homology of the different parts of this compositional parabolic Hilbert scheme. And the action of GLR, one can explicitly get using correspondences again. Okay, any questions? Okay, now we can do the following trick. We can fix n, which is the rank of the group in the theoretic algebra, and we can let m go to infinity. From the geometric side, what we're gonna have is the non-reduced curve, which is given by y to the n is equal to 0. From the algebraic side, what we're gonna get is the theoretic algebra now with parameters 0, 1, because letting c go to infinity is the same thing as letting t go to 0. Essentially, you can rescale and let t go to 0. So we can take a limit of our results, and we get an action of the theoretic algebra on the equivalent homology of this non-reduced curve. That now will be the polynomial representation of this theoretic algebra with parameters 0, 1. And going to the spherical subalgebra, I have an action of the spherical rational theoretic algebra on the equivalent homology of the Hilbert scheme of this non-reduced curve. That again gives you the polynomial representation of the spherical theoretic algebra. And you will notice that there is no part C here. I don't have a Gieseker statement here. The reason is that in the proof of the Gieseker statement, there is this flip in the parameters m and n, and it doesn't make sense anymore to fix n and let m go to infinity, because now m becomes the rank of the group, and it doesn't really make sense. However, there should be a way, there should be a statement for Gieseker, And a possible way to get this element for Gieseker is to put this into a more general context of Coulomb branches. So now I go with the, I guess, physics part. I'm told this is physics, I don't know. So given a reductive group that acts on a vector space, there is a beautiful construction of Breberman, Fickelberg, and Nakajima of a Poisson algebra, commutative Poisson algebra, whose spectrum is known as a Coulomb branch. I don't want to go too deep into this, but this is modeled after the equivariant homology of the Affine-Grassmannian. When we take loop rotation into account, we get a natural quantization that we call a Coulomb branch algebra. And this construction can be generalized. It was generalized by Ben Webster to account for non-trivial line defects, whatever this means. This is physics, supposedly. It's basically a parahoric version of a BFN construction. What we do is, besides this data of G and N, I'm going to take a parahoric subgroup inside GO. Let me just remind you here that O is formal power series in a variable T, and K is formal Laurent series in this variable T. And Ben Webster and Webster's construction depend on choosing a parahoric subgroup and a subspace inside NK that is stabilized IP. This subspace has to be nice enough. I don't want to say what that means, but in the examples we have, this space is nice enough. And all the algebras that we have are either BFN Coulomb branch algebras or Webster's generalization of BFN Coulomb branch algebras. For the spherical Theoretic algebra, what we have is the Coulomb branch for G, which is GLN, acting on the adjoint plus the fundamental representation. If you want, this is the representation space of the following quiver. This is a 1. Okay. And I have an action of GLN here. Let me draw this differently. The 1 is here. Okay. And it is a result of Kodera, Nakajima, and Webster that we get the spherical rational Theoretic algebra when we run this BFN construction. Moreover, we can get the full rational Theoretic algebra using this generalized Webster's construction. Now we have to choose a parahoric subgroup, which is going to be the standard Iwahori, and a subspace which is stabilized by this standard Iwahori. In this case, it's going to be the Lie algebra of the Iwahori, plus again, the fundamental representation, the power series in T. And the Quantization algebra is also a Coulomb branch, a BFN Coulomb branch, where now I take GLN to the R acting on this vector space in a way that we get the representation space of the following quiver. So here I have N, many N's. This is R N's and framing, which is 1. So this is like a symplectic dual description of the Quantization algebra. So I guess I should put more arrows here. This is the cyclic quiver with R vertices. So all the algebras that we have turn out to be Coulomb branch algebras. And there is a recent very beautiful Springer theory for Coulomb branch algebras that was developed by Hilbert, Kemnitzer, and Weeks and generalized to the parahoric setting by Gardner and Kivinen. Well, we have a notion of generalized Affine-Springer fiber, which is on as follows. Remember that we have the data of G and N. And for the general situation, we also have a parahoric subgroup and a space stabilized by this parahoric subgroup. I will consider all those spaces in this affine, it's not an affine Grassmannian or this. Well, when P, for example, is GO, I have the affine Grassmannian. When P is standard Iwahori, I have the affine flag variety that satisfy these conditions. So I just want, essentially, have a projection to L of the space that you use to define the BFN algebra, and I take the fibers over that projection. Under my assumptions on this space, sorry, of this element V in NK, we have an action of the generalized Coulomb branch algebra on the equivariant homology of the generalized affine Springer fiber. And all the Hilbert schemes that we have talked about turn out to be generalized affine Springer fibers. So I need to give you an element in the corresponding representation spaces. Remember that, for example, for the Theoretic algebra, I have that N is GLN plus C to the N. I need to give you an element in NK, which is going to be this element. And it is not too surprising that it is this element, because I can write the algebra of functions and C, at C, and just write as formal power series in X, and then I adjoined, well, 1 y squared up to y to the n minus 1. Remember, y to the n is equal to x to the m. And this matrix Y is precisely the action of Y when I give this presentation, okay? So the Hilbert scheme by a theorem of Gardner and Kivinen is the Springer fiber for this element, which is again in N. Oops, it's not writing, okay. But here again, N is GLN plus C to the N. The parabolic Hilbert scheme is this generalized affine Springer fiber when I take a parachotic subgroup into account. And the compositional parabolic Hilbert scheme, and again, let me point out that here I do have Y, is going to be this generalized affine Springer fiber, where now remember that my representation space, sorry, my representation N is the representation space of the cyclic quiver. So what I am going to do, well, I guess I have Kn. Kn. I have RKNs, and here I have the framing. What I'm going to do is I'm going to put identities everywhere, except in this last guy where I put Y. This is the interesting part. And here is the same vector B, which is just 1, 0, 0, 0. It turns out that this generalized affine Springer fiber is the compositional parabolic Hilbert scheme. And then our results essentially follow from this BFN Springer theory. And we can match the action that was constructed very explicitly by Gardner and Kivinen. We can match it with our action, at least in the Hilbert scheme and the parabolic Hilbert scheme side. And in all this story, I don't need that N and M are co-prime. So we get corresponding results in the non-co-prime case. However, it is not so nice. We don't know explicitly what representation we get in the non-co-prime case. For sure, it will no longer be irreducible. It is, for example, non-irreducible when M and N are both equal to 2. We conjecture that even though it is no longer simple, it is still semi-simple. And it has minimal support. Minimal support essentially means that all these algebras have a unique maximal two-sided ideal. It means that the annihilator is that unique maximal two-sided ideal. Evidence for the conjecture is that this would match formulas of Etting of Gorski and Losev on representations with minimal support. And that this result, that is joint work with Pavel Ettinghoff, Vasily Krylov, and Ivan Losev, where we construct representations of Gieseker starting from representations of full Theoretic with this flip of parameters. This is valid for representations with minimal support. What I gave you before is just a special case of this. So this match between representations of Gieseker and of Fulcher-Ednik carries over to minimal support. And all these compositional parabolic punctual Hilbert schemes on any plane curve is a generalized Affine-Springer fiber. The idea is more or less the same. You take the matrix Y that is going to be given by the action of Y on the algebra of functions, of geners of functions around 0. So we get an action of Cherednik algebras and spherical Cherednik algebras and Gieseker algebras on parabolic Hilbert schemes of any curve. In particular, we get it for this non-reduced curve. According to BFN-Springer theory, there should be an action of the algebra of functions now on this variety. So here what I have is not a quantization of the Gieseker algebra, but a deformation of it. Where remember that to define the Gieseker variety, I have the equation commutator of AB plus IJ is equal to 0. I deform it slightly and now I have it equal to 1. You can also get this as some sort of flavor deformed Coulomb branch. So there should be an action of the algebra of functions here on the equivalent homology of the compositional parabolic Hilbert scheme. When R is equal to 1, we just recover the action of the spherical Cherednik algebra, which in this case is commutative, and it is the algebra of functions on this Calogero-Moser space. And I don't know if this is in any way related to the representation of the full Cherednik algebra on the equivalent homology of P Hill. And you'll notice I didn't specify X or Y because it's not very clear to me what should be in here. My intuition tells you that it should be related. I just don't know exactly how. So I will leave you there, and thank you so much for your attention.